gave you, and I'll use the board as I see good for you. Who knows already a lot about creep? Good. So you apply a constant load, and then you have deformation that happens over time. It's not typical with metals at ambient temperature unless you have lead or another low melting point alloy. So lead pipes, if you go to Cambridge University in England, they sag, and it wasn't looking like that after the installation. It's the effect of the heating water circulating through it and creating that creep deformation. When you creep, I mean, we talked about it for plastic, so it's not anything that new to you, but for metals in particular, initially, so say we look here at the, I'm going to call it the plastic deformation. So obviously when you apply the load, you have Hooke's law, you have some elastic deformation, and then after that, over time, you get that plasticity. So you start initially, and your rate of deformation is going down. This is concave shape towards the bottom. It's a negative convexity. And what happens is you are exhausting the easy sites for deformation. So if you had a few dislocations here and there that were just about to move when you apply the load, now over time they will. But there's only so many of those sites. And that's why eventually you reach this regime of what we call secondary creep. What's interesting there is that the deformation rate is constant. It may happen for a long period of time or a short period of time, depending on your temperature and your material, how much of this constant rate you're going to have. For polymers, this portion here, we talk about viscoelasticity and stuff. With metals, it's a little bit the same story. Again, it's just small reorganizations that eventually lead you to an increment of strain, but it's not something that you can't have a constant source of this deformation mechanism. When you come in this regime here, it means you have a constant supply of deformation sites, if you will, and we're going to go through what these are. Eventually, you reach the third regime where now you accelerate, and this could be due to a number of things. Microvoids is a common source when you reach a certain amount of plasticity, where you had little inclusion imperfections. You have voids that are going to start to grow to a significant size, start to coalesce together, and then you are less resisting to the deformation. Eventually you crack and fracture. If we go back to our lecture on steel, we talked about fracture toughness. So when you reach this condition here, typically you have a crack, and it's at a length that makes the overload condition, that meets the overload condition. And that stress intensity factor is not too much dependent on the overall history. You can essentially use your stress intensity factor. Yes?
So they have those curves that show rupture life. Is that the point that you're showing? Is that what they're considered for rupture?
Yes. So if you do a rupture life, it won't be a stress intensity as much. So it will just be what your stress level is. So S as a function of time. And if you have less load, you're going to last longer. So this one is going to look like this, a little bit like an SN curve. So this point here for the fracture corresponds to a certain load and give you only 1 point on this plot. And you can construct that. What I would say right away, we're going to talk a little bit about alloys that are used for turbine engines. And what happens there is you're more limited by the amount of strain that you can tolerate in your design than by that fracture. Not in all the conditions, but there are blades that if they fit so tight in the shroud that if they elongate 2%, now you have a big interference. And they do put a little bit of a seal that wears away. So you have, say, a honeycomb, a metallic honeycomb structure, something that's soft and easy to machine off by the blade to keep that air gap very tight. But there's still going to be so much you're going to be able to do that honeycomb can't be too thick. Otherwise, it'd be crushed easily. So sometimes this idea of a creep rupture is good. Sometimes it's really a question of figuring out how much deformation you're going to get. With plastics, that's often the case from what we discussed before. For metal, it's a mixture. It really depends on the application. So we're going to talk a little bit more about this regime 2 here where the rate is constant. And that's the next slide I have for you. I'm putting up a very complex map. Temperature, normalized stress. So if we do it this way, because so say you have the shear stress here, so this is maximum in stress going to lower value. So that's for our stress level, and that's here our temperature, normalized temperature, T over the melting temperature. So here you're really hot and you're colder here. You can see from this plot the first curve that comes for what we call creep. So it looks a little bit like this, where you have more or less of the uniaxial loading response. This is rapid loading. When you see this first intersection here for cobalt creep, you are already here at about 0.35 of the melting point. What does that mean? It gives us some indication that below that temperature, your strain rate would be less than 10 to the minus 10 per second. Very, 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 very slow. So that's where we were talking. Typically, we consider half the melting point as where creep starts. This chart starts at 0.35, but it's a very, very low rate. So these first curves you see are for a regime, that cobalt creep regime. What happens in cobalt creep is very different from what happens above here where you have the Nabarro creep. So you have Nabarro creep, last like this. All right. So you have grains in your material. Your metal here. The grains, for now, let's say that they are stable. In other words, you're not at a temperature. A lot of grains microstructure, you heat them up and they recrystallize and they change. But this is not what we're talking about here. We're talking about a certain grain structure and what happens when you apply the tension. So I apply a tension this way on the microstructure, going down. One way that the material will stretch over time is by moving some of the atoms that are on this grain boundary and then move them to the other grain boundary. I have to be careful here about. And that's our cobalt creep. It happens in the low temperature side, and therefore you don't have a whole lot of vibration to make that diffusion. This is a diffusion process. You're asking the atoms to relocate from this position to this position, and they'll do it naturally because there's a driving force. Over here, there's a little bit more spacing in that boundary than there is in the other one because of the tension. Now, I say there's little vibration, meaning that it'd be really hard for these atoms to diffuse through the grain, because the grain essentially is very solid, doesn't have too many vacancies. You need vacancies for diffusion. These are just holes in the crystal. But in the grain boundary, you have availability of space. It's not perfectly organized, so there's more space for the movement. So if I start moving atoms randomly, they go back and forth, then they get here, they realize there's more space, so eventually your grain will elongate. And that's how you get your permanent deformation in this regime of creep. You can already think that one way to reduce it is to make the grains bigger. If you make the grains bigger, you have a bigger average travel distance from this location to around here, and your creep rate's going down. Now I made this line here that goes to, if you go to the slide, the Nabarro creep. What happens at a certain temperature is you not only going to diffuse to the grain boundaries, but your diffusion in the grain will become more significant. So start taking material from this whole area and bring it over here, bring it over there, through the grain as opposed to the grain boundary. And the rates for this condition are higher. What happens is you just have a whole lot more of a channel for transferring the material than what you had when everything had to go through the grain boundary. The grain boundary is really, really thin, and now you're talking about a volume diffusion. So to the extent that the volume diffusion, it can happen because now you're hot enough, it literally goes through the grain. This process also you can inhibit if you make bigger grains. It's the same idea we had before. There are some alloys that work on the energy of the grain boundaries to minimize this cobalt creep. So you just put some alloying element that will make the arrangement of the atoms more stable here, less energy, less opening, and therefore you're reducing that creep. But if you pass above this critical temperature, it doesn't matter anymore, because now you're becoming dominated by diffusion in the bulk. So it's the kind of ideas that I want to circulate around for creep. There's a third regime that's around here with higher stress. And this becomes a little closer to what happens during a tensile test. You have the dislocations that participate in the deformation, with the difference that you also have a recovery of these dislocations. So you're forming them, and then at the same time you recombine them to reduce your defect density. So in this range of temperature, you can be deforming and you can think of it as you always have about the same amount of dislocations. So some of them just come and some of them recombine and disappear. At the limit, it's not that different than from ambient temperature, it's just a different speed. At ambient temperature, when you deform a metal, you'll reach a point where you have so many dislocations that you don't have hardening anymore. It will take a long time. It may be 200–300% strain before you reach that steady state region. But in that steady state region, you start really to recombine defects. It just happens to be here at much lower strain values. As far as the concept, that's what I wanted to illustrate. I have a plot. It's the 6th slide, the last one on that page, where I'm showing a similar plot to what we have here, but it's with respect to the grain size. Just to emphasize that grains do play a significant role on how the rate of this process is going to take place, and people have taken the care to quantify it. Any question on basics of creep? Yes?
So did you say dislocation creep is recoverable? Does that mean it's like elastic strain?
The question was about the creep and whether it was similar to elastic strain. It's not so much that it's a plastic deformation process, because you really have the dislocations moving. But what happens at the same time, another location, 2 other dislocations get back together. And that's why I don't really want to call it elastic, because there's a permanent change. And that's why you get a permanent deformation and a permanent elongation. The only thing that remains more or less the same is your density of dislocation. So you don't have any hardening anymore. That's why you keep deforming over time. If you had the hardening we have at ambient temperature, everything will stop. Good question. Anything else? All right, let's see what we can do with the turbine engines. I already talked about it a little bit. So you have a compressor side, you have the combustion, and then you have the turbines behind that are essentially driving everything. They're driving back the compression, and that's why you have the axle between them, and everything is very optimized for maximum temperature. So what happens is you get more thermodynamic efficiency if you have a high burning temperature. You start from a certain temperature, the coolest possible, and you go to the highest possible. How you design in terms of cost and performance depends on the application. There are turbines that have blades that are used for steam application. You have them for hydropower. So when we talk about blades in general, it's very general. On the turbine engine, you have them on the compression side. These tend not to be coated. And after the combustion, you typically need them to be as coated as possible. What happens for the turbine blade, you can have on that chart, the 4th on the page, so many failure mechanisms. So I have oxidation, creep, hot corrosion, fatigue, and we obviously have creep, and you have to design for all of that. People have looked into designing material for use at higher and higher temperatures since approximately the 60s. And the first category was the superalloy, a little bit what we talked about, trying to make the grains bigger, trying to make single grains parts. And then one of the breakthrough was really the use of the coating. It doesn't show because if you go from the superalloy, they terminate it with intermetallics. These didn't really work too well. People have been really worried about fracture toughness. So the chart for superalloys pretty much ends where the one with ceramic coated superalloy starts. So you're looking to these days at very high temperature in the engine, and the way to accommodate it is the best metal you can find, and then you have to protect it against the temperature and the oxidation. So that's where the concept of the barrier comes into play. You need toughness, you need fatigue resistance, you need creep resistance. So this is driven not so much by weight. You wish you have a low weight alloy, but in the end you can essentially work with the design to have a very, they make these structures hollow with reinforcement, not like a honeycomb, but a little bit like a reinforced shell, and that way you can adjust the thickness with the strength that you have. So if we think about how we make a single crystal, so that's the second slide on page 3. What you try to do from the beginning, you have the whole mold. So say I'm putting up a blade that's very simple here, and there's essentially a selector, they call it the helix here, and your starting point here. So what you do, you fill the whole mold with the metal. So everything is really hot, and then you start to solidify from the bottom. So you control the temperature, you solidify from the bottom. You have a bunch of nucleation sites that start right here on the surface. The grains that grow the fastest here will essentially make their way through the spiral more rapidly, and at the end you'll end up with a very specific orientation of the grain for that alloy, and it will gradually grow from one end to the other. There are issues with alloying. So some alloys will essentially, as you solidify, will try to push back the alloying element in front of you because it's harder to fit them in the solid than in the liquid. So you have to set your speed so you don't give it the chance to do all that separation. You want to have it homogeneous. There's only so slow you can go and make this work correctly. So say you made it into a single crystal, and these can be, you know, of sizable shape. You essentially can avoid a lot of the creep mechanisms that we've been talking about. It doesn't take away from the dislocation aspect, because even if this is a single crystal, it does have a bunch of dislocations in it, and it actually, when you deform it plastically, it will not behave in as good of a way as a polycrystal. So the deformation is going to tend to localize in specific planes. So you try to avoid that. You still try to essentially avoid a creep on those components to the extent you can. So one way to resist creep better, Then on the third image, I'm showing you oxide dispersion. It's another way to maximize the resistance to creep. This time you get a dispersion of oxides that is stable at the high temperature, because sometimes you can form precipitates. We've talked about it in aluminum alloy. We talked about aging. But if you do something like this with aluminum, they just disappear when you heat up because they become in solution. So these oxides need to be stable and also coherent. By coherent, I mean that they are more or less part of the microstructure. They're not a separate, completely separate entity. Once you have those, you essentially can inhibit the movement of dislocation a lot. And that's how you increase your creep resistance. So I remember being surprised by the amount of these oxide. It can go to about 70 volume%. So it's more or less of metal matrix composite by itself, but it's called a superalloy.
Most OPS steels were like 0.1%.
Yeah,
Oxide.
yeah, but
Really low, I thought.
no, you see the image. The reason for it, you don't need to put a whole lot of alloying to create that phase. So in terms of chemistry, it's not 70% oxide, but it forms a lot of it, and the oxide that takes more volume and all that. So it's essentially a way to increase the creep. Obviously, when you do that, all your toughness and everything else going down with it. So there are limitations to it. I gave you a chart collected a while ago about the different alloys. Essentially says the single crystal is a technology of the 80s, more or less. Before that, they were doing directional. So directional is a little bit the same idea, where you try to get a gradient in temperature, but you don't just grow a single grain. You grow multiple grains that will have an elongated shape like this. So if I try to deform this, I just really have a greater distance to go from taking the material here and putting it to the tip. So it's a greater distance than if this is equiax of the same size. And you can make these bigger as well just by, it's easy to make them directional by a temperature gradient here. They compete with each other. So instead of having the selector, you start here and they just compete and keep growing. So there's been a lot of work trying to increase the surface temperature. And I want to show you where things are more or less with those technologies. You have a coating. The idea of the coating, that's the last slide on page 3, is to provide an oxidation and corrosion resistance and also a thermal insulation. The way the temperature profile works on the surface of the blade, so say we're going to put here, I'll call it distance, because I really don't want to put a 0 or something like that. Say this is where the coating start, coating end, and this is where we have our metal. So what happens is they set the air temperature right now around 1500. It could be higher in some cases. before you reach the coating, the temperature drops. And I don't really have all the scale for how much temperature the coating is exposed to, but you have a first drop, you drop it again through the coating, and here, I mean, you don't want to be more than about 1200. So you're looking at a 300 degree temperature drop in continuous operation. I mean, if this was transient, it'd be easier. But the fact that this runs continuously makes it hard to maintain a difference here between the coating and the metal temperature. One way to do it is this layer that I haven't really talked about too much. It's a little film of air that it's air that's coming out the surface of the turbine blade. So if you have your turbine blade looking from the top, it's going down like this, leading edge. You'll have little holes, very little, close to the leading edge. You can put them anywhere you want, but the idea of those is they'll distribute an air film that because of the speed of rotation will form a boundary layer. So the boundary layer is essentially more of a viscous flow, so it's hard for the combustion gas that are coming in at 1500 to reach the surface of the coating. Now there may be some anomalies with the pattern here, and in some cases you can have a local burn, true. But the idea is still to lower the air temperature from the gas that's within a millimeter from the surface of the blade to the gas that's actually touching your coating. It's not something that you have to do all the time. There are designs with, especially on the again on the compression side, where it's hot, but it's not as hot to require it. There are issues, obviously, with making holes in terms of the quality of the coating around it, and essentially it can be site to initiate delamination. This is more or less the operation. So what I wanted to focus on, we talked about the metal, I want to talk a little bit about the coating. The two coatings that I want to talk to you about are made in different ways. We have one made by vapor deposition, and that's the first on the fourth page. You see all the orientation. It's very columnar, and it's also very loose between them. It's not that different from an anodized layer that you have on aluminum. So porous, columnar. This coating will be able to withstand a differential in thermal expansion. It's relatively flexible. On the other hand, it's not the perfect barrier, because from a thermal standpoint, you have a direct connection to transport the heat down. You also have a risk of bringing combustion gases down, air and penetration. So when they do that, they need a very high quality bound layer. So you have this coating, but you have a bound layer that will protect against oxidation and corrosion, your metal that's underneath of it. It's common. The bound layers just needs to be better quality. typically use it also in the second case. So what I'm showing you on the right image is a thermal spray coating. The thermal spray coating is essentially droplets of molded ceramics. So they come down flat on the surface and they form these splotch. And you can form a bunch of them. They essentially stack in different ways. And your orientation is more or less the opposite than what we had by vapor disposition here. The idea of this one, it's relatively easy to do. You need a special plasma torch to melt particles, project them on the surface. Your microstructure may not have the perfect bond with the substrate here or a bound layer, but one of the advantages, you have little air gaps between the layers. So this, say, here is an air gap. Maybe I have a little air gap there. So in terms of thermal protection, it's more insulating than this type of microstructure. In terms of resisting a differential thermal expansion, so a tension and compression going this way, it's really not as good. So you can have a lot of issues of cracking. When you build this microstructure, typically you have a lot of residual stresses. It's a little bit like welding, because you have a cold substrate and you're building up on top of it with something that's hot. It's going to cool down and create shrinkage forces. So you have to pick, and the both technologies are out there, and there's actually a lot of competition as far as who's doing what. I gave you a plot that's presenting different chemistries you can use for making these coatings. What I really want to touch on is this thermal spray process. The reason is, we talk about material selection, and sometimes you can use a material that you would not use otherwise just by coating it. If it's not all of it, it could be just part of it. So say you have to connect a piece of stainless steel to a piece of regular steel, and at the connection you may have a lot of moisture. You can coat your steel with zinc or stainless at that end and just get away from a galvanic effect in that area. I've done that before. So the general process for this, the name is thermal spray. You can do it either with particles or with a wire. A wire feedstock is cheaper, and that would be sufficient for doing what we're talking about, putting some stainless steel or some zinc. The way they do zinc galvanizing on an existing bridge, for example, or installation, is they're going to use wires of zinc and melt it by arc and project it and form all this complex microstructure. For this type of coating here with ceramics, it's not, you need a microstructure that's so specific. Sometimes they'll mix different powders to get a different effect, so they want to have some small with some big ones to fill the holes and do all sorts of things. So typically be a particulate feedstock, and you can heat it up by plasma or by flame. The flame the flame is more for metals. So for our ceramics will be plasma, but the idea is with the particle, you heat them up. If you melt them, now you're at risk for oxidation and all sorts of issues. So some people would actually, for metals, say copper, you can thermal spray copper without melting it. So in that case, you don't have as much oxidation. And you can use a shielding gas as well. So it's a very, very versatile tool, and people have been thinking about making free forms out of it, but it's not super fast, and it will always have those residual stresses that we talked about. Well, thank you, and I'm sorry for the computer issue.